So let's move to the next subject, which was the first session on ADS. Mike Seidel from PSI will summarize what happened in the session. Use this and speak close to the mic.
Okay. Thank you, Jean-Pierre. So I will summarize the session number 9 on high-intensity accelerators and ADS systems. And actually, I have only 3 slides to let you know. On this first slide, I review what has been said in the presentations very briefly. So Jean-Pierre Leval opened this session with a review presentation on ADS, and he formulated the goals that a high-intensity accelerator should fulfill to be used for ADS systems. So he claimed a power between 1 and 10 megawatt to begin with. Then, of course, we need low losses in this accelerator. And to give you an idea about the losses, I think about 100 watts per location is an acceptable loss. So that's in the range of 10 to the minus 4 to 10 to the minus 5 for a high-intensity accelerator. Then, of course, reliability is very important. We discussed this, and I will say something more about it later. And stability is also an important issue, because with the power of your accelerator, you control the power of the reactor, and therefore it's very important to keep the beam power very constant. And then, last but not least, cost is important. So then we had presentations by Alex Müller and Frederick Booley, and they concentrated on the superconducting LINAC technology. Actually, Alex Müller gave an overview of all accelerator concepts, but then he concluded that a superconducting LINAC technology is the right way to go. And I think important developments were worked out already for the Mirror project. That's an important practical step to come closer to a realization of an ADS system. So this technology is well advanced. And one of the important advantages is that within the LINAC you can have some redundancy. For example, if you have 80 cavities and one cavity fails, then you can try to compensate this with other cavities in the LINAC. Then we had a presentation by Pierre Mandrion about new cyclotron concepts. So he quoted a concept which is developed at present by Peter McIntyre from the Texas A&M University. He proposes many innovations in this cyclotron, but it's only a paper study at the moment. So it's a superconducting magnet, superconducting cavities, stacked cyclotrons where you have several cyclotrons on top of each other, so parallel beams, and strong focusing. And then he focused on another proposal by himself or by the IMA collaboration, and that is a so-called reverse valley cyclotron, where one could accelerate H2 plus ions, which can be more easily extracted by stripping. And because of the reverse bending in this cyclotron, there is an easy way to extract the beam from the cyclotron, because the extracted beam is then pointed to an outward direction, and not as in other concepts, the extracted beam has to pass through the whole cyclotron. Then we had the presentation by Roger Barlow. He focused on the Daedalus, also an H2 plus cyclotron concept, where the highest power machine is aimed at 4.5 megawatt on average. And yeah, this concept also uses H2 plus ions for easy extraction, but here the extraction path crosses the cyclotron, as I mentioned already, which makes some complication because the extraction path goes through all the end fields of the magnets. And then he also showed us some FFHE concepts that use strong focusing, and FFHEs have a large acceptance, which is an advantage there. So in summary, what is good? What is the status of the field? What is good? We can say that 5 to 10 megawatt beam production is within reach of today's technology. And this is also demonstrated, for example, by the ESS project, the European Spallation Source in Lund, which is going for a 5 megawatt beam. And this is a well-advanced project already. And then what we could identify, one of the major problems is the reliability and the number of beam trips. So today, the standard of these high-intensity accelerators that are actually operated is between 10 and 100 trips per day. So that's my own facility at PSI. It's about 30 trips per day. or the experience at the spallation neutron source in the US that uses actually a superconducting LINAC, which has about 100 trips per day. But the goal for ADS is much lower, so it's between 1 trip every 100 days or maybe 1 trip every 10 days. So there are about 3 orders of magnitude between these numbers, what we have today and what we are aiming for. And even if you don't know anything about accelerators, you can imagine that it's very difficult to improve a technology by 3 orders of magnitude. That's true for every technology. So on this next slide, I have a table comparing the different concepts in accelerator physics which could be used to produce a high-intensity beam. So we have the cyclotron, superconducting LINAC, rapid cycling synchrotron, and fixed focus alternating gradient accelerator. So the 2 major concepts are here. It's the cyclotron and the superconducting LINAC. And today we have some examples of those machines which are running. So at PSI, we operate a cyclotron-based facility with a record beam power of 1.4 megawatt. This was demonstrated over a period of like 5 days, so over a long time scale. And normally we run at 1.3 megawatt. SNS in the US has just reached a power of 1.2 megawatt, but typically they run below 1 megawatt in order to get a better lifetime for their liquid metal target. Then rapid cycling synchrotron is used in the JPark facility with a design power of 1 megawatt. At the moment they have reached 300 kilowatt. And FFHE, there's only realizations today with very low beam power, so I didn't quote it here. So let's go through the pros and cons a little bit of these accelerators. So some of them are cyclic accelerators. In cyclic accelerators, you use your expensive amplifier chain and your expensive accelerating structure several times to accelerate your beam. And this gives you immediately an idea about cost efficiency, right? Because you use these expensive items several times. So cyclic accelerators are basically cost efficient. Of course, in detail, one has to calculate how much it really costs, but it's different from a LINAC. So the cyclic have a relatively low cost. The efficiency for cyclotrons is relatively high. So at PSI, we achieve 80% efficiency, which means from the power we take from the grid, we convert 18% into beam power of the proton beam. And it's relatively compact, the cyclotron. The disadvantage is that the energy is limited. So we think about 1 GeV is the absolute limit, but at 1 GeV it already gets rather difficult. So 800 MeV would be better. Extraction is always difficult if you do it with a septum, of course, due to the losses in the septum, but also if you use these ions and stripping extraction, it's also not straightforward, because the foils then have a high power density on the foils, and the lifetime may be not very long of these foils. And then there's also some tedious tuning involved, which the LINAC, for example, doesn't have, because it's a straight beamline. Cyclotron has bending magnets, and this means tedious tuning before you have these very low losses in the 10 to the minus 4 range. So for the LINAC, that has the lowest losses. So an L-band superconducting cavity has an aperture like this. So the beam stays far away from any wall, and this naturally means the losses are very low in a LINAC. It can achieve an arbitrary high energy by making it longer, right? And then also you can realize some redundancy, as I said already, by replacing faulty cavities with other ones. But the LINAC solution is expensive. Superconducting cavities are expensive. You need a cryoplant for that. The efficiency is typically relatively low because, for fundamental reasons, RF frequencies produce losses even in superconducting material. So, and even if you have very small losses at low temperature, this has to be compensated. So, for example, if you had at 2 Kelvin, if you had 1 watt losses, then you need at room temperature 1 kilowatt to compensate these small losses at low temperature. So that's a fundamental thing about LINACs, that the cooling power needs to be relatively high, especially if it's operated in CW. And then the couplers are technologically difficult, but that can be solved. I mean, couplers with high power that transfer high RF power to the structure. So rapid cycling synchrotron is a pulse machine, therefore we can immediately conclude that's likely not suited for very high power. So 1 megawatt is a respectable number, but very high power is difficult. And FFHE has, the practical aspects have not been worked out. So the assessment here is basically that cyclotrons and superconducting Linux are today the ways one could go. And I would say a Linux is an obvious solution today with details already worked out, but it's expensive. The cyclotron, the PSI cyclotron, for example, this concept could be scaled, I think, for 3 megawatt, maybe even to 5 megawatt. So that's another way to go. But all these concepts which we have seen in the presentations are very good attempts, very good concepts, but they have not been worked out yet in detail. So we cannot compare the cost at the moment, and they are not ready to be built in the very near future, I would say. Okay, so I come to the summary then. So one important point that we, I think, observed at this conference is that new concepts should be developed and evaluated continuously to reduce the cost of these high-intensity facilities. But the comparative assessment, which concept is the better one, that's actually difficult to do it in an objective way. Yeah. Everyone who has experience in a certain field, of course, tries to push his concept. So in that situation, for example, between Linux and cyclotrons, that reminded me a bit about the situation we had some 10 years ago in the community of the linear collider, where warm accelerating, normal conducting copper structures were standing against superconducting accelerator structures. And at that time, the community has created a committee out of 12 experts, which was called International Technology Recommendation Panel. And this commission did evaluate the different concepts over 1 year or so, and then came to a conclusion, to a recommendation, which technology is the right way to go. And maybe that's a concept which is relatively objective, which could also be used in this community here. So today we have to state that superconducting Linux are most advanced but need further optimization, for example, with respect to the energy efficiency and the chip frequency. But I also want to say that despite of this healthy competition, which I mentioned here in this first point, it's very important that the community should coherently support those projects which are already in an advanced stage. So for example, Mura should be supported by all people in this community in a coherent way. And we should not try for such projects that are already advanced to discuss again the fundamentals, what is the right way to go. Yeah, that's basically all I wanted to say.
Thank you, Mike. So, do we have questions or comments? Yes. Please state your name and institution.
Jacques Maillard from CNRS, France. I think that there are fundamental parameters for the future of ADS, is the efficiency. But the efficiency for ADS must be thinking as global. It means you have the source of neutrons, the spallation source, and you have the accelerator. And what is important to fix a K effective as low as possible, that is the goal of ADS, is to have a K effective as low as possible, is the global efficiency on the source.
No, I think I want to correct you. I don't think the ADS is to have a K effective as low as possible. It's to have whatever K effective you need for the system you want to design.
I think
you mean just less than 1? Yes, but yes, not as low as possible.
No, but as low I intend to have 95. Not 998, it was very dangerous. You have to have at least something like 97, 96, better 95, 0.95. And in this case, you have a certain possibility of increase, for example, or decrease the energy. And the problem is the efficiency of the accelerator. And with some parameter, we can move. We can increase by a factor 2 the energy when it is necessary.
No, I'm sorry, the energy is not an issue. I think there was an experiment that showed that you have optimum energy below 1 GV. There's no issue of energy.
It's linear, and you can choose for safety reasons or for other things to decrease or increase the energy. It's a parameter, the energy. And
yes.
What I would like to say, to ask, but it's not the answer, if the efficiency of accelerator keep at 20%, the future of ADS is very low. When it is 50, as people of India say, in this case, you have a huge, or more than 50%, it has a huge future. The crucial parameter, I think, is the efficiency of the other parameters are more technological, but that is, there are perhaps physical limits about the efficiency. If there are physical limits on efficiency, it means there are perhaps no future for ADS.
Okay, well, I mean, I'm not an accelerator expert, but I do understand that actually when you go to higher power stored in the beam, you go towards higher efficiencies. I don't know exactly what the limit will be, but there are a number of people who are confident that high efficiencies can be obtained. Mike, you might want to make a comment on this.
So really high efficiency above 50% is probably very difficult or physically not possible, right? Because what you have to do is you take power from the grid, you convert it to a DC voltage. There you lose already 5 to 10%, and you convert to RF power. The best klystrons have 65% of efficiency, and then you transfer it to the beam where you again lose some factor. So if you multiply this all together, it's very difficult to get above 50%. But I think you can compensate this with the right choice of this criticality value. I'm not an expert on the reactor, but I think there is some room to maneuver. Maybe some expert wants to comment on this.
Yeah. So anyway, if you look at some of the presentations, and my presentation, for example, you can see the playoff between beam power and K effective. So let's go to the next question. Could you state your name and institution and speak closer to the mic, please?
So in your first slide, you were mentioning ESS as a good example of a modern machine which produces lots of megawatts. But actually, ESS is a 2.5 GV machine. So I'm not sure, at least to my knowledge, that our reactor colleagues would like to have 2.5 GV beam in their reactor. At least that's what I heard in my lab. So if you decrease ESS to energy level, which we have heard about, which is 1 GV or so, then you will be left with 2 megawatts, which is the energy scale which you get from fixed field rings, okay? Like your ring in PSI. The second comment, which is the last column of your table on the slide 2, that concerns FFAG. So there you mention CW, which is a hot topic, that's correct nowadays about FFAG optics, that application. So I would like to stress something which has been mentioned in the talks by Roger Barlow, for instance. There has been 2 experiments of CW acceleration in FFAG lattices. One was the linear lattice. That's a FFAG prototype FFAG, which has been built at Daresbury, tested the past 3-4 years. They use CW, a fixed frequency RF, and they did CW acceleration of electrons in this model. Second example concerns the other type of FFAG optics which these guys are trying to push in that application, again, which is the 1950s type of optics, which is called scaling optics. Prototype of, again, electron machine has been constructed and tested in Japan. It uses the serpentine type of acceleration that, again, Roger Barlow has been showing, which, again, uses fixed frequency. And so, again, they got CW acceleration type there.
Okay, Francois, thank you very much for this comment. I tried to be careful with my assessment. I said the details are not worked out, and this is what I meant with it. I'm aware of the attempts to provide CW operation, right? But there's a long way to go before you really can produce a high-intensity beam.
Okay, I think, sorry, but...
We lack something very important during this meeting. It's as important as we understand from the previous intervention as the reactor side of these discussions. We need ADS accelerator review, because we know it's going to cost of the order of 10% of the reactor power. I think this meeting needs serious accelerator review.
On demande rien.
Pierre.
Okay, Pierre, on demande rien. A mic?
Quickly reminding you some key point in my presentation about cyclotrons, I would like to underline the following fact. Our design is aiming at finding a solution for a very simple ADS driver. But what I mean by simple? Simple for me is mono-stage machine, a single-stage machine, very easy to operate. Not tedious matching between different stages, etc., etc. This is something that we have to avoid. Even for cyclotron is possible. This is one of the key points of the design I have presented in this conference.
Yeah.
Thank you.
Actually, I mentioned that on the first slide. I said internal sources, and this is what you basically...
Sorry, Mike, it's not internal. It's external access injection line.
Okay, but no injector. I mean,
No injector.
no explicit
Without injector. This